Now, with my big pleasure, let me introduce our last plenary talk, Professor Pavlo Etingof from the Massachusetts Institute of Technology of USA, who will tell us about the theory in tensor categories with applications to modular representation theory. You're welcome, Professor Pavlo.
Okay, thank you very much. I am very pleased to speak at this conference. It means a lot to me. Just a second, let me share my screen again.
We can see.
Yeah, I'll share again because it's yes. So this is based on my joint work with Victor Ostrich, who just spoke, and Kevin Coulombier. And this is essentially a continuation of Victor's talk. So I will really explain the techniques behind proofs of such results, as he explained, using the theory of tensor categories. So just to remind, at the end of his talk, Victor talked about this number of, so he talked about the number of indecomposable summands in a tensor power of representation in characteristic P, let's say of a finite group, which is coprime to P. And he introduced an invariant, which is the limit when n goes to infinity of the number of these summands in b to the n raised to power 1 over n. And this is a non-negative real number, which limit exists. And the theorem that he stated is that this function extends to a character of the split Grothendieck ring, which means that it's additive and multiplicative. Split, which is also called green ring, which is has a basis of indecomposable representations, and multiplication is defined by taking tensor product and decomposing in direct sum of indecomposables. And then there is also a statement that the number, well, Victor calls it delta of V, I call it D of V, is an algebraic integer, and moreover, algebraic integer of very specific kind. If Q is e to the pi I over P, root of unity of order 2P, then we can define the Q number, which is Q to the M minus Q to the minus M over Q minus Q inverse. And then the dimension, this growth dimension, D of V, is a linear combination of such Q numbers with non-negative integer coefficients. Okay, so he explained this example with Z mod 5, where we obtain the golden ratio. Now, my goal is to explain how this type of theorem, and as well as some theorems that he stated at the very end, on more refined asymptotics of these lengths, these numbers of summands, non-negligible summands in tensor powers, summands of dimension not divisible by P, how to prove such results. And this is based on the theory of tensor categories. So I will start with a short introduction to this theory. So first I want to recall that a definition of symmetric tensor category. Well, I won't actually recall the actual definition because it's kind of long and rather technical if you do it from scratch. but I will remind the main features and the main axioms just in passing. So first of all, we have a field K, which is algebraically closed. A symmetric tensor category, first of all, will be a K-linear abelian category, which means that it's an abelian category, and its home spaces are vector spaces over K. Compositions, of course, are bilinear of morphisms. Moreover, I want the category to be Artinian, which means that objects have finite length and home spaces are finite dimensional. And this means that this is a category equivalent to the category of comodules over some coalgebra. Also, I want to, so this is kind of what it looks like as an additive category. And then there is also a multiplicative structure, which is the tensor product. So I want it to be a monoidal category, which means that it has a tensor product functor. You can tensor objects. This should satisfy associativity, which in the category case is a structure. You have to give associativity isomorphism, which is supposed to satisfy the pentagon relation. There should be a unit object. Also, I want it to be a symmetric monoidal category, which means that I have a flip map, which squares to the identity and which satisfy hexagon relations, which means that if you flip X with the product Y1 times Y2, either from the left or from the right, then it is the same as to flip it first with Y1 and then with Y2. And finally, I want the category to be rigid, which means it has duality functor. X goes to X dual, which satisfies some rigidity axioms. So these are the multiplicative structures in this category. And is an algebra, usually if you put on a set or category an additive structure and a multiplicative structure, then you want to have some axiom connecting them, which is usually called distributivity. And here we also put this axiom by saying that tensor product of morphisms is bilinear. And finally, there is a little axiom, which is not very restrictive, which says that endomorphisms of the unit object is the ground field K. In fact, if you don't impose this axiom, all you get is direct sums of such things where this axiom is satisfied. So basically, this is not a restriction at all. And if you have such structures and properties, then your category is called a symmetric tensor category over K. And so this definition is obtained by looking at a category of finite dimensional representations of a group and trying to abstract away the group and only keep the categorical information. And so no surprise that the most basic example is the category of representations of a group over the field K. This is a category of all finite dimensional representations. They have all these structures. They have abelian structure. They have tensor product. They have duals and so on. And in fact, the most basic example of this is when the group is trivial, then you obtain just the category of finite dimensional vector spaces over K. So this is the simplest possible symmetric tensor category. And in fact, we don't have to take a group. We could take some more general objects, such as affine group scheme, this include and take representation category of this affine group scheme. And this will include all the examples like, you know, Lie algebra, for example. So, and then the second example, which is different actually from the previous ones, is the category of supervector spaces, which is mentioned in several talks already today and before. This category is defined when characteristic of K is not equal to, otherwise it is just the same as vector spaces. And this is the category of Z-mod 2 graded vector spaces. So an object there is a direct sum of V0 and V1, where V0 and V1 are both finite dimensional vector spaces. And it is is the same as the category of Z mod 2 graded vector spaces, or what is the same representations of Z mod 2, except for one aspect, which is that the flip map is not the usual flip map, but it is the usual flip map composed with the sign. So if you flip two homogeneous vectors x and y, which lie either in V0 or in V1, then the flip map is supplemented with a sign -1 to the power degree of x times degree of y. So the only time this is going to be non-trivial is when both vectors are odd and lie in V1. But this makes this category, so all the axioms are still satisfied, but it makes this category different from the previous examples. So once you have this example, you can generalize it, and you can consider categories of finite dimensional representations of affine supergroup schemes over K. So what is an affine group scheme? This means that you have a commutative Hopf algebra of functions on G, and you look at the comodules over this Hopf algebra, and so you can. So these are representations of an affine group scheme, and you can do the same with Hopf superalgebras. So Hopf superalgebra is just a Hopf algebra. Commutative Hopf superalgebra is just a commutative Hopf algebra inside this category super vector spaces over K. So actually, see, here we start seeing an important feature, which is that symmetric tensor category is a good home for doing any kind of algebra. So any kind of multilinear algebra makes sense in a symmetric tensor category. And so in particular, we can do this in super vec K, and we have a notion of a commutative Hopf algebra. And in the ordinary sense, it will not be commutative, but will be super commutative, which means that xy equals to -yx if x and y are both odd. But nevertheless, we can consider its category of comodules, and this will be a symmetric tensor category. And there is a slightly more general thing that one can do, which is that you can take the group, or any supergroup has a group of points over your ground field K. That's an ordinary group, and it is just homomorphisms from O of G to K. That's an ordinary group, and we say that an element Z is a parity element if it squares to the identity and acts on, if you act with it by conjugation on functions on G, then it acts by parity. And then you can define the following category: representations of G, comma Z. It is the category of representations of G on super vector spaces in which this element Z acts by the parity operator. And this is the most general kind of category you can obtain in this way, in a sense that will become clear in a few minutes. So to say that precisely, I want to make the following definition. So category, symmetric category, tensor category C is called Tanakian if it admits what is called the fiber functor, which is by definition an exact symmetric tensor functor from this category to the most basic tensor category, which is vector spaces over K. Well, it is clear what exact functor means because these are abelian categories, and also, but what symmetric, what a tensor functor means needs to be explained. So this is actually not a property, but an additional structure. It just means that you have an isomorphism of functors f of x tensored with f of y with f of x times y. And this isomorphism should satisfy, it's a functorial isomorphism, it should satisfy some commutative diagram with the associativity isomorphism in C. So this is a way to make sense of saying that this functor preserves the tensor product. So preserving the tensor product is actually a structure that we need to introduce. And symmetric is also if you have this J, you can say what it needs to preserve the flip. It should commute with the flip maps. It is known that if such a functor exists, then it is unique up to an isomorphism. This was proved in the paper by Delaney and Milne, Tanakian categories. And moreover, you can reconstruct your group G. So you can define a certain group G, a fine group scheme G, which is the tensor automorphisms of F. So this group is defined as follows. So it's you can define its algebra of functions. This is the so-called co-end of F. But you can also discuss this group in the language of Grothendieck functor of points. So this means that for every commutative algebra you should be able to say what is points of G over this algebra. And this is simply actual automorphisms of F, but with extended scalar to this algebra. And so maybe I can write this as G of A, and algebra A is just automorphisms preserving tensor product F with extended scalars to for A in the category of commutative algebras over K. And moreover, the category C is reconstructed as the category of representations of G. So actually, the category determines a group G, a fine group scheme G, such that it's representations of G, and G is uniquely determined and exists. So that's the story with Tanakian categories. So Tanakian categories are representation categories of affine group schemes. And in a similar way, we can define the notion of a super Tanakian category. So this is a representation category of a super group scheme. More precisely, we call a category C super Tanakian if there exists a fiber functor from C to super vector spaces over K. And in this case, this functor is unique, also up to isomorphism. And we can define the supergroup scheme of automorphisms of F in a similar way, which is an affine supergroup scheme over K. And there is also a parity automorphism, which naturally exists here. This is just the parity. It acts on every F of X as the parity map. And you get that the category is determined by, the category is the representation category of G, Z. And this pair GZ is determined uniquely up to inner automorphisms. By the way, I should say when I say that the functor is unique, it's unique, but up to a non-unique isomorphism. And there is a good example of this when your category is the category of local systems of finite dimensional vector spaces over some topological space X. Let's say connected topological space X. In this case, so this is a symmetric tensor category because you can pointwise tensor vector spaces, so locally constant sheets of vector spaces, local systems of vector spaces. But and the fiber functor is taking the fiber of this locally constant sheet for a local system at a point. Well, there is no canonical choice of the point. So for different points, you get different fiber functors, but they're actually isomorphic. So if you have a path on your connected space, pathwise connected space, connecting 2 points, this gives you an isomorphism between those functors. But if you take a different path, which is not homotopic to the original path, you get a different isomorphisms. So these functors are isomorphic, but not canonically isomorphic. And now I want to make a definition that the category C has moderate growth if when you take object X and C and raise it to nth power, this takes us closer to Victor-Stock, then the length of X tensor n, which is the number of composition factors, is bounded by some constant Cx to the power n. So obviously, any object in a Tannakian or super Tannakian category has moderate growth because we can realize it on a vector space, finite dimensional vector space, and then we can just take this constant to be the dimension of this vector space. And in the super case, as Victor mentioned, it will be just ordinary dimension, not the super dimension. So it will be the sum of even and dimension of the even and the dimension of the odd part. But on the other hand, there are categories which are not of moderate growth, and the quintessential example is the Deligne category rep GLT, for example, which is the interpolation of representation category of general linear groups to a non-integer value of t. So Deligne and Milne described this example in their paper on Tannakian categories, and then later there were many papers studying their structures. This is very interesting. But this is beside the point for my talk, because I'll be interested in categories of moderate growth. And Deligne proved a great theorem about 20 or slightly more years ago, which is that in characteristic zero for categories of moderate growth, in fact, there is nothing else compared to what I already explained. So a symmetric tensor category over a field of characteristic zero is super Tannakian if and only if it is of moderate growth. When one direction is clear, as I said, if it is super Tannakian, it is of moderate growth. It is the opposite direction that is non-trivial, this direction here, that every symmetric tensor category of moderate growth in characteristic zero is a representation category of a supergroup with some parity element Z. And that's a deep theorem. And in fact, to prove our results on growth, we had to generalize this theorem to positive characteristic. And the problem is that in positive characteristic, this theorem is false, as stated. And its failure in characteristic P and the ways to fix this failure are central to proving the growth results that were explained in Victor's talk. So to explain how it fails and how this can be fixed, I need to discuss the notion of semi-simplification of a symmetric tensor category. And this is the following. So actually, you can semi-simplify more general categories, which do not have to be abelian. You just need to have an additive, rigid, symmetric monoidal category. Still want tensor product to be distributive, and the morphisms of the unit to be K, but you do not require it to be abelian. But you still want it to be a Krull-Schmidt category, let's say. So home space is a finite dimension. So every object is uniquely a direct sum of indecomposables. And then there is an important notion of trace of a morphism. That doesn't even require these finiteness assumptions. So it's a notion of trace of a morphism from an object to itself. And so the trace is an element of the ground field K, and it is defined in the following way. So I mentioned that my category is rigid, which means you have a duality functor, and duality functor comes through with evaluation and co-evaluation maps. So a co-evaluation map is a morphism from 1 to X tensor X dual, and the evaluation map is X dual tensor X to 1. And so if you have a morphism from X to X, then you can draw the following diagram. So you start with 1, and you co-evaluate into X tensor X dual. Then you act by F in the first factor, X, and you end up again in X tensor X dual. And then you flip. So you go to X dual tensor X. And finally, you evaluate and you go back to 1. And the composition is a morphism from 1 to 1 which is according to our axioms is a number in K. So that's called the trace of F. So you can observe that if you do it to a vector space and write it in a basis, that's exactly the definition of trace of a matrix. And if you do it for super vector spaces, then because of the sign in the flip map, this is going to recover the super trace, which is trace of the even block of the matrix minus the trace of the odd block. And then in particular, we can define the categorical dimension of X, which is the trace of the identity morphism from X to itself. So again, for representations, it will be the dimension regarded as an element of K. And for super representations, it will be the super dimension regarded as an element of K. And now an important notion is that of a negligible morphism. So a morphism F from X to Y in such a category is called negligible if for every morphism the other way from Y to X, trace of the composition is 0. So or trace GF is 0. It is equivalent because trace of GF equals to trace of FG. And then the first lemma says that negligible morphisms form a tensor ideal, which means it's a collection of subspaces in home spaces of the category, which is closed under composition with any morphism and also under tensor product with any morphism on any side. Now, if you have a tensor ideal, you can define a quotient by this tensor ideal, which is the same category with the same objects, but morphisms are quotient of home xy over n xy. But in general, this category won't have very good properties, but under a very simple assumption that it will have very good properties. And this is the content of lemma 2, which says that suppose our category has the following property, that the trace of any nilpotent endomorphism is 0. This is not a very strong restriction at all, although it can fail in examples, because, for example, if your category is abelian, if it is a symmetric tensor category, then this is automatic because you can consider the filtration of your object by kernels of powers of your endomorphisms. And with respect to this filtration, this endomorphism is written as a block upper triangular, strictly upper triangular matrix. So its trace will be 0 because it will be the sum of traces of diagonal blocks. And even if your category is not abelian, but merely admits a monoidal functor, need not be exact or faithful, just a monoidal functor into an abelian symmetric tensor category, then this is still true because you can compute trace after applying the functor. And so if this mild condition is satisfied, then the lemma says that the quotient category, which is a priori just a monoidal category, so the quotient category, as I said, has the same objects, but morphisms are obtained by taking morphisms on the original category and quotiented by n of xy, is not only a monoidal category, but it is actually a symmetric tensor category. So it is abelian, even if the original category was not abelian. And moreover, it is semi-simple, which means that we have complete reducibility in this category. Every object is a direct sum of simple objects, is a direct sum of the objects that occur in its composition series. So, these lemmas are not difficult. And then there is a third lemma, which is the most interesting one, which was proved in some very old paper by Dave Benson in early 1980s, but in a different language. And it says that under this assumption here, you can describe what it means for a morphism to be negligible. In fact, it's more convenient to describe what it means for a morphism from X to Y to be not negligible. This is equivalent to saying that it is, first of all, an isomorphism, and the second dimension of X is not zero. In other words, so the only way a morphism can fail to be negligible is by being an isomorphism on an object of non-zero dimension. And also, if you have a morphism between decomposable objects, and you split it into a matrix of morphisms between indecomposable summands, Fij, then this morphism is negligible if and only if all the Fij are negligible for all I and j. And so I should have said that this category C bar, which is C mod n, is called the semi-simplification of C. And so we know it's a symmetric tensor category. And this lemma implies that what happens is that, well, like if you take endomorphism algebra of an object X, which is indecomposable, it's a local finite dimensional algebra. So it's a direct sum of the field K and the maximal ideal, which is the nil radical of this algebra. And this lemma says that the entire nil radical consists of negligible morphisms, and the remaining identity morphism, scalar morphisms, are also negligible if dimension is zero, but they are not negligible if dimension is not zero. So this means that when we quotient out, and also morphism between different indecomposables are all negligible, because they cannot be isomorphisms. And so this means that when we quotient out negligible morphisms, we actually have very few morphisms left. We have no morphisms between different indecomposables other than zero, and we have only scalar morphisms from an object indecomposable to itself. And moreover, if that object has zero dimension, then we actually have also only the zero morphism. So that means this object itself is zero, turns into zero when you pass to quotient. And so this corollary says that simple objects of C bar are therefore indecomposables of C of non-zero dimension. The objects of zero dimensions get killed. And so here is an example of how that works in a specific situation. This is an example that Victor already considered for p equal 5. So you have representations of Z mod P in characteristic P. And then, as Victor mentioned, this can be written, group algebra of this group is generated by G such that G to the P equals 1, which in characteristic P can be written as G minus 1 to the P equals 0. And this has indecomposables J1 through JP, which are Jordan blocks of sizes 1 through P. And now all these their dimensions are 1, 2, 3 up to P. So in particular, for the last one, JP, the dimension is 0. And it gets killed when we go to semi-simplification. So in the semi-simplification, we are going to have only P minus 1 simple objects from L1, which is the unit, to LP minus 1, coming from J1 through JP minus 1. And JP gets killed. And then you can compute the tensor product. So you know that when you tensor Jordan blocks over complex numbers, they tensor in the same way as representations of SL2. So they tensor by the so-called Clebsch-Gordon rule. Because any nilpotent matrix can be uniquely extended to a representation of SL2. Well, Clebsch-Gordon rule is this tensor product rule, but without those two numbers here. So what you get when you tensor in characteristic P and also kill this JP, you obtain a truncation of the Clebsch-Gordon rule. So when n and m are very small compared to P, you get the usual Clebsch-Gordon rule. But then when they get larger, it gets truncated. And the truncation is that you sum these things not to minimum mn, but to minimum mn, p minus m, and p minus. And this is actually the so-called Berlinde algebra, which arises in two-dimensional conformal field theory in physics, For mathematicians, this is just the fusion rule for a finely algebra SL2 hat at level p minus 2, or equivalently, tensor product rule for the quantum group, semi-simplification of quantum group at root of unity, Q, which is e to the pi I over p. And so this is, we call it Verlinde category because it categorifies this Verlinde algebra in conformal field theory, except that our category is over complex numbers. Physics category is over complex numbers, but our category is in characteristic P, and the physics category is braided, but our category is symmetric. In fact, this category is a reduction of this physics category modular P. So the category that arises in physics is in fact defined over the cyclotomic ring of root of unity of order P. And if you reduce mod P, or rather mod some fractional power of P, you obtain this category. And the braiding becomes trivial. So for example, and the variant of this is instead of Z mod P, you can consider, for example, alpha P, which is the Frobenius kernel of the additive group, and you will get the same result. So Ver2 has just one object, J1, so it is the category of vector spaces. The Ver3 has J1 and J2 squared, according to this rule, is so L1 and L2 squared is L1. So you get the category of super vector spaces and characteristic 3. But in Ver5, we have this object X, which is L3. And so as Victor, so this X tensor X, so Victor said that J3 tensor J3 is J1 plus J3 plus J5, but J5 drops out and you just get J1 plus J3. So you obtain this tensor product rule. And so in general, this Ver P is tensor product of super vector spaces if P is bigger than 2, with Ver P plus, which are all the spanned by all the Li's with odd I. And so this shows in particular that this the Lin's theorem fails in characteristic 5 because Verlinde 5 has no fiber functor. Because if there were a fiber functor, it would map X to a certain vector space, and the dimension of this vector space would have to satisfy this equation, d squared equals to d plus 1. And that equation doesn't have integer solutions, even no rational solutions. So, so this is a counterexample to the Lin's theorem characteristic P. And another construction of Ver P, which is how it actually appeared in 1990s, is in the work of Sergei Gelfand and David Kazhdan, and also Georgiev and Mateo. And this is by semi-simplifying the category of tilting modules for SL2, which Victor mentioned in his talk. This category is not abelian, but it satisfies the requirements that I needed, and we can define its semi-simplification, so we get the same result. And now we can talk about how to fix the Lin's theorem. So yeah, so the way to fix the Lin's theorem actually turns out, so like with super vector spaces, we had a new category of super vector spaces which were not Tanakian, and then we generalized by looking at all categories which fiber over that category. And similarly here, since Ver P doesn't fiber over any of the categories we know, we should make a target of fiber functors. This was Victor's idea from 2015. And he asked which categories can be fibered over Ver P. So perhaps the Lin's theorem is true if you replace the category of super vector spaces by this Ver P. And he proved this in the case of fusion categories, which are semi-simple tensor categories with finitely many simple objects. So this means that every tensor category, which is any fusion category in characteristic P, which is symmetric, can be written as representation category of some group, but the group is internal to this category. So in order to understand such categories, we would have to study groups that live inside this category, Lie algebras that live inside this category. That's a very interesting problem by itself, which I don't have time to talk about. And then we will understand all such categories. And then Victor conjectured that this was true for general symmetric tensor categories originally, but soon it became clear that for non-semi-simple tensor categories, this is not true. But for semi-simple categories, miraculously, it did turn out to be true. And so I will skip this counterexample for the non-semi-simple case. But so in fact, there is a more general class of categories which are called Frobenius exact, on which the so-called Frobenius functor, which I didn't define, is exact. And this includes, of course, semi-simple categories, because on semi-simple categories, all functors, additive functors, are exact. And the main theorem of this work in 2021, which published in the Annals with Colombier and Ostrich, is that the Deligne theorem can be generalized to characteristic P in the following way: that the categories in characteristic P, the category of is Frobenius exact and of moderate growth if and only if it admits a fiber functor to ver P, and this functor is unique. So if Frobenius exact and moderate growth is equivalent to being representation category of a group that lives inside of an affine group scheme that lives inside this ver P. And so this in particular holds for semi-simple categories. And so now in the last maybe couple of minutes, I explain how this can be used to prove those growth estimates. So actually, having this theorem, it becomes very simple. So you look at the category of representations of G, where you want to compute those growth parameters, and you consider it semi-simplification, which is rep bar K of G. And then remember that what happens is all indecomposables of dimensions divisible by P become 0 when you do semi-simplification, and those of dimension not divisible by P remain. But the category is semi-simple now. So there means that this dn of x, which is the number of summands in x to the n of dimension not divisible by P, can be interpreted simply as the length of the corresponding object in the semi-simplification. So the number of summand or length, because it's a semi-simple category here. But now the main theorem that we proved says that we have a fiber functor from rep K of G to ver P. And this means that we might try to compute not the length of this object, but rather the length of the image of this object, f of x to the n, f of x bar to the n. Well, that is not exactly the same thing, because when you take a functor, fiber functor, the length, there are more morphisms in the target, so this length can grow. But it turns out you can show that it doesn't grow too much. It grows by a sub-exponential factor, which means that when you take nth root, actually the limits, even though this is less than this, but the limits of these sequences are the same. And then you can compute this parameter inside the category of supervectors, inside the category of Verlinde P. And there you just get a sum of Li's. And the corresponding number is simply the largest, well, it tells us these representations multiply according to this Verlinde rule. So for each of them, you can write a matrix by which you need to multiply. And for L2, for example, it is this matrix and so on. And all you have to do is find the largest eigenvalue of this matrix. That would be the gross dimension D of Y. And of course, this largest eigenvalue in this case is simply a character of the Verlinde algebra, which is positive on every basis vector. And it sends every Li into its quantum dimension, which is this Mi, which is this I sub q. So you get that your growth dimension is the sum of mi times I sub q. In particular, it's an algebraic number. And this is somehow the key for getting all those bounds. And then if you want to get more precise bound, you need to have a more more understanding of what this tensor category is like. So it turns out it's a representation category of a linearly reductive group scheme. Linearly reductive groups are classified by Nagata's theorem, and that but then in VRP there are some more examples, and there is a conjecture about what they are. And if we prove this conjecture, we can get rid of this quadratic exponential factor in the last slide of Victor's talk. Okay, thank you very much.
Thank you. Thank you very much.